Hi everyone, in this video we'll be talking about mixed inhibition. As the name suggests, it looks like it is a mixture of two different kind of inhibition paradigm, and in this video we will look at that. So under normal conditions we know enzyme interacts with substrate, forms an enzyme substrate transient complex which ultimately give rise to enzyme and product, and the enzyme remains unchanged and we get the product, right? But under a condition of mixed inhibition, the enzyme substrate forms enzyme substrate complex, but the inhibitor can either bind to the enzyme substrate complex or it might bind to the enzyme competing with the substrate as well. And as a net result, the product formation does not take place. So we can see here the inhibitor can operate in two regimes. One is like an uncompetitive inhibitor. Instead of binding to the enzyme directly, it binds to the enzyme substrate complex. And second regime, it can also operate like a competitive inhibitor. So that's why it is known as mixed inhibition. Let's try to understand the mixed inhibition and try to derive the Michaelis-Menten equation under these circumstances. So here is the equation. Now Ki and Ki dash are the red constants for these two possibilities of inhibitor binding. Now first we try to write the expression for Ki and Ki dash. Now with the laws of equilibrium we can derive these expressions, right? From there we'll now write it in a different format, like EI is E into inhibitor concentration divided by the red constant Ki. Same for here, we would write the expression like this, and in a moment it would be clear why we are writing, and we would be using this formulation later. Now we know that under these circumstances there are four species. First, the enzyme alone. Second, the enzyme with inhibitor only. Third, the enzyme substrate complex. And fourth, the enzyme in a format of enzyme substrate and inhibitor complex. So the total enzyme is like combination of all of these. Now from here we can start deriving our equation, and now we know what is the concentration of EI because we have already written this notation, and also we know what is the concentration of ESI means. After that we can further formulate it and do a little bit math, and we would arrive into this situation. Now in order to shorten this equation we can assume that 1 by I plus K1 is alpha, and 1 by I divided by Ki dash is alpha dash, and as a result we come to a situation like this. Now if we multiply both the sides with K2, we know that K2ES means V0 and K2ET means Vmax, and then rearranging the thing give us the equation like this. Now this is the equation for mixed inhibition. Now this is how the kinetic data look like in normal situation of Michaelis-Menten equation, which is like this, where the slope is Km by Vmax, and this equation is a straight line plotted in 1 by V versus 1 by S scale. Now, and the intercept is 1 by Vmax. Now in this situation of mixed inhibition, both the slope and the intercept has changed. You can clearly see the slope has increased, that's why the line becomes steeper, and the intercept is also different, and the intercept has increased, suggesting the Vmax has decreased, right? And the intercept becomes alpha dashed by Vmax. So clearly we can understand this kind of inhibition reduce the Vmax to a factor of alpha dash, and with the increase of value of alpha dash the line becomes steeper and steeper and the inhibition becomes stronger and stronger. Now there could be two type of decrease in Km. Either the Km could be greater than the Km apparent, or the Km might be lesser, and both is possible for this kind of inhibition. Now if the Km is greater than the apparent Km, that means it more closely mimics the competitive binding. Now if the Km is like lesser than the Km apparent is lesser than the Km, then what happens is it more mimics the uncompetitive binding. Now, one of the special case of mixed inhibition is non-competitive inhibition, where our both reaction constants ki and ki dashed are equal. That means alpha and alpha dashed are equal. So here is the Michaelis-Menten equation, how it looks like in a V versus S plot. Now clearly there would be a decrease in Vmax, but the Km remains the same in this condition. And here is how the Line-Weaver plot look like under non-competitive inhibition. Now remember, non-competitive inhibition is one of the special case of mixed inhibition. In this situation, these lines would meet at a point -1 by Km in the x-axis, and the intercept would be more because the Vmax has decreased to a degree of Vmax by alpha, and that is how the non-competitive inhibition looks like in a plot of Line-Weaver. Let us take an example of non-competitive inhibition. Cyanide can be a non-competitive inhibitor of cytochrome C oxidase, and that's why it could be detrimental for us. And that was pretty much discussion about the the mixed inhibition and one of the special case of mixed inhibition, which is non-competitive inhibition. I hope you enjoyed this video and this video was informative enough. So if you like this video, give it a quick thumbs up. Don't forget to like, share and subscribe. Thank you.